June 29, 2026. Today, the world of physics is buzzing with news that seems ripped from the pages of a science fiction novel. Researchers have just announced the first evidence that our planet and the universe around us are awash in a background of spacetime undulations called gravitational waves. This isn't the sudden jolt from a single violent event, like the black hole mergers we've detected before. This is a constant low-frequency hum, a cosmic chorus created by the slow dance of supermassive black hole pairs throughout the universe. It's a discovery that promises to answer some of the most profound mysteries about the nature of these cosmic giants. But as we stand on the precipice of this new understanding, it's worth remembering that today also marks the anniversary of a total solar eclipse that, 99 years ago, provided one of the most dramatic confirmations of a theory that completely rewrote our understanding of gravity, space, and time. It is a story of science, of perseverance, and of a man who, despite facing unimaginable hardship, helped to change the world. On June 29, 1927, a total solar eclipse carved a path across the far northern reaches of Europe and Asia. The path of totality swept across the United Kingdom, Norway, Sweden, Finland, and into the Soviet Union. For a fleeting 50 seconds, the moon completely obscured the sun, plunging the landscape into an eerie daytime darkness. For the astronomers who had journeyed to these remote locations, this was not just a spectacle. It was an opportunity to perform a crucial test of one of the most radical scientific ideas ever conceived, Albert Einstein's theory of general relativity. Just 8 years earlier, in 1919, another total solar eclipse had made Einstein a household name. That eclipse, observed by Arthur Eddington, had provided the first compelling evidence that gravity, as Einstein proposed, was not a force but a curvature of spacetime itself. The theory predicted that light from distant stars passing near the sun would be bent by this curvature. During a total eclipse, when the sun's blinding light is blocked, these stars become visible, and their apparent position can be measured. The 1919 measurements matched Einstein's predictions, catapulting him to international fame. But the scientific community, particularly in Germany, was not entirely convinced. The measurements were difficult, and some argued the evidence was not definitive. The 1927 eclipse was another chance to put Einstein's theory to the test. This is where the story takes a turn that is both inspiring and tragic. Among the astronomers preparing for the 1927 eclipse was a young German scientist named Erwin Finlay Freundlich. Freundlich was a passionate advocate for Einstein's work and had been trying to verify the theory for years. He had led an expedition to observe the 1914 eclipse in Russia, but the outbreak of the First World War had led to his internment and the confiscation of his equipment. His efforts in 1919 were similarly thwarted. For Freundlich, the 1927 eclipse was personal. He was determined to succeed where he had failed before. He organized a major expedition to northern Sweden, one of the best locations to see the eclipse. He assembled a team of skilled observers and brought the most advanced photographic equipment available. Freundlich was meticulous, driven by a passion for science and a belief in the beauty of Einstein's vision. However, the story of the 1927 eclipse is not a simple tale of triumph. The path of totality was narrow, and the weather was famously unpredictable in the far north. Many astronomers were disappointed. A report in the journal Nature captured the sense of personal disappointment of the astronomers who were prevented by clouds from observing the total eclipse. Freundlich's expedition was one of those that faced the devastating blow of cloud cover. After all his years of struggle, he was denied the clear skies he so desperately needed. Now, why does this matter? Why tell the story of an eclipse that was, in many ways, a failure? Because, as Richard Feynman taught us, science is not a straight line to success. It is a messy human endeavor full of setbacks, disappointments, and wrong turns. Feynman himself experienced plenty of failures. His famous O-ring investigation after the Challenger disaster was a masterclass in persistence, but it followed a career filled with problems that didn't work out as planned. The beauty of science, Feynman would argue, lies not in the final triumphant result, but in the process. It's the willingness to try, to fail, and to try again. It's the courage to ask a question, even when the answer is elusive. The story of the 1927 eclipse is a perfect example of this spirit. Even though Freundlich's expedition was thwarted by clouds, his dedication was not in vain. He had helped to build the instruments, train the observers, and keep the scientific question alive. Other astronomers on that same day were more fortunate. Their observations, combined with data from other eclipses, continued to build the case for general relativity. Eventually, the evidence became so overwhelming that Einstein's theory was accepted as one of the pillars of modern physics. But there is an even deeper connection here, one that ties directly to the discovery announced today. The gravitational waves we are now detecting are the most extreme prediction of Einstein's theory. They are ripples in the very fabric of spacetime, created by the most massive and violent events in the universe. The fact that we can now detect a constant background hum of these waves, a gravitational wave background, is a testament to how far we have come. It is a direct confirmation of Einstein's vision, a vision that was being tested, debated, and confirmed during that cloudy day in 1927. It also shows the power of technology and persistence. The scientist who made this announcement on June 29, 2026, didn't just look up at the sky. They built massive, incredibly sensitive instruments like the LIGO and Virgo detectors, and spent years analyzing data. They had to account for every possible source of noise, from seismic tremors to quantum fluctuations, to isolate this faint cosmic signal. Their success is built on the shoulders of giants like Einstein and Freundlich, and it embodies the same relentless curiosity that drove them. And it's this relentless curiosity that is the true legacy of Richard Feynman. Feynman was not a man of grand, sweeping theories like Einstein. He was a man of the nuts and bolts, the calculations, the path integrals. He was a man who loved to take things apart and see how they worked. He would have been fascinated by the gravitational wave background, not just because it confirms a theory, but because it represents a new way of seeing the universe. He would have been excited by the technical challenges, the engineering marvels that made the detection possible. And he would have been deeply respectful of the human story, the decades of work, the collaborations, and the occasional failures that led to this success. So, on this day, June 29, 2026, we are witnessing a convergence of past and present. We have the announcement of a new discovery that opens a window onto the hidden dynamics of the cosmos, a discovery that validates the work of a century ago. And we have the memory of a total solar eclipse in 1927, an event that, despite its difficulties, helped to solidify the very theory that predicted these gravitational waves. It's a reminder that science is a conversation across time. The questions we ask today are the same questions that have driven humanity for centuries. What is the universe made of? How does it work? What is our place within it? The answers are not always easy, and the path to discovery is often paved with clouds. But as Richard Feynman would remind us, the beauty is in the asking. The beauty is in the relentless pursuit of understanding, even when the answer seems just out of reach. Whether it's a scientist in 1927 staring at a cloudy sky or a team in 2026 analyzing data from a gravitational wave detector, the spirit is the same. It's the spirit of curiosity, of perseverance, and of the unwavering belief that the universe is worth understanding. Now you might be thinking, this is all well and good, but what does it have to do with me? The answer is everything. Because this story is a metaphor for our own lives. We all face our own personal eclipses, moments when our plans are obscured by clouds, when our efforts seem to amount to nothing. The temptation is to give up, to assume that our questions will never be answered. But the lesson from the history of science is to keep going. The clouds will eventually part. The signal will eventually emerge from the noise. The key is to remain curious, to keep asking questions, and to be willing to try again. That is the Feynman way. It's a way of living that is not afraid of failure, but embraces it as a necessary part of the journey. It's a way of living that finds joy not just in the destination, but in the process of discovery itself. The gravitational wave background announced today is not an end point. It is a new beginning. It opens up a new window to explore the universe, allowing us to study the formation and evolution of galaxies in ways that were previously impossible. It could even help us understand the nature of dark matter and dark energy. The questions that this discovery raises are just as important as the ones it answers. And that is the beauty of science. Every answer leads to a new question. Every discovery opens up a new frontier. So, as we reflect on this day, let us celebrate not just the successes, but the struggles. Let us celebrate the scientists who braved the cold and the clouds to test Einstein's theory. Let us celebrate the teams who spent years building and refining the detectors that can now hear the whispers of colliding black holes. And let us celebrate the enduring legacy of Richard Feynman, a man who taught us that the most important thing is to never stop asking why. The universe is a vast and mysterious place, and we are only just beginning to understand it. Stay curious,